Good day, everyone, and welcome to today's Lightbend webinar from March 22nd, 2018, titled Concept Drift, Monitoring Model Quality in Streaming ML Applications. My name is Oliver White. I'm Chief Storyteller and MC at Lightbend. And joining me today is my colleague, Emre Velipashalo, who is our principal data scientist here at Lightbend and my #1 person to go to when I have questions about mathematics or electrical engineering. While I let everyone get settled in, I'd like to ask our audience a quick poll question. At this stage in your journey towards developing fast data and streaming and machine learning applications, which of the following would be the most helpful? So if you are an onophile, who is someone who loves wine, then finding a bottle of Chateau Mouton Rothschild from 1945 would make you pretty excited. However, machine learning algorithms don't exactly get better with age. The fact is that most of these algorithms are designed to work with stationary data, and the reality in our true lives is that streaming data is rarely stationary. So what begins to happen over time is termed concept drift, where models based on data collected within a fixed time period begin to suffer from a loss of prediction quality. Now, what most people do to handle concept drift is periodically retraining the models with new data, where the length of the period is usually determined based on the costs of retraining. Yet these changes in the input data and the quality of predictions are not monitored, so it's actually difficult to determine the real cost of inaccurate predictions. Emre is joining us today to discuss a better alternative, which is monitoring model quality by testing the inputs and predictions for changes over time and using change points in retraining decisions. So in this webinar, Emre will spend some time reviewing the successful methods of machine learned model quality monitoring. Today's webinar is made possible only by Lightbend's hundreds of happy customers, including our client Rewards Network, a company that has provided nearly 100,000 businesses with financial and marketing services in the restaurant industry. If you're in or around the Chicago area, Rewards Network is looking for a senior Scala engineer to help build a new platform using lots of cool tech. You can find out more about this position and other open positions with our customers and partners on our website under the Company tab. Many of you always ask if this webinar is being recorded, and as always it is, and will be shared with you next week. If you do have questions for Emre today, feel free to add them to the Questions tab in the GoToWebinar control panel, and we'll see if we can get around to them in today's session. Of course, if you are an existing Lightbend subscriber, then you know that you can directly access our expert engineers through the customer portal and ask all of your additional technical questions, how-tos, what-ifs, and best practices there. So that's all I have to say for today. Let's hand it over to Emre and give him a warm and silent welcome. Hey, Emre, thanks for joining us.
Hey, thanks for the great intro. I'll try to keep the math to a certain level. More pictures, hopefully. So let's start with a couple of questions. Why should we monitor the quality of our machine learned models in operation? So that's the question for this presentation. Well, George Box once said, all models, but some are useful. Since you released your machine learned model to operation, you know that it was useful at some point. The question is it still useful? It's been a while. And if it is not useful, wouldn't you want to know when to update it? Or in other words, is that Royal Stilton, or is it some stinking old cheddar in production? So here's the core problem. Machine learning assumes the data generating distribution stays the same. In other words, the examples that we see in the training set should resemble the observations we will see in operation. Here I have a toy problem, a classification between desk lamps and floor lamps. I will keep going back to this example over the course of the presentation. Streams are rarely stationary. So let's say we have a stream and with the initial observations, we developed a classification model. Later on, we may see a population change. Maybe there's a trend in our data. This renders the classification boundary suboptimal. Maybe there is a spontaneous change, maybe a failure in the sensors. Either way, this is called concept drift. There may be an object that we have not seen before, or we have seen before and forgotten. This is called an emerging concept. Whatever the reason for the change, these types of changes affect the model performance and cause it to degrade. The common solution to this problem is by training the machine learning models over batches of new data periodically. So here I have a longer version of the stream, and it may turn out that the change doesn't occur for a long while. So here the population drift happens and the concept drift happens in the last two batches. Within the batches in between, the model performance is not degrading. So even if I retrain the data, the model coefficients will not change, most probably. So I'm wasting modeling time. And if I'm using a supervised method to train my model, I'm wasting labeling effort. If I try to save this cost and do not train frequently enough, I may miss the change point and my model becomes ineffective, and there will be cost in prediction losses. Can active learning help? It's designed to deal with reducing the labeling costs. The way it works is it picks an example from the classifier margin, requests the label for this example, and updates the classifier margin according to the label, and thereby saves us labeling costs. In this toy example, we saved one label, but in practice, we save many more labels. But the problem is it's not designed to handle concept drift that falls outside of the classifier margin. And it's ill-equipped, or it's not designed to handle new concepts at all. It's designed for reducing the labeling costs in stationary learning environments, and it cannot deal with concept drift. What is a better way? A better solution, we're looking for changes in the classifier performance, is to try to deduce this from observing the changes in data and predictions. So for this purpose, we add a monitoring block into our diagram. We can monitor the input data, we can monitor the features, we can monitor the predictions, and if we have labels, we can monitor the prediction errors. Some monitoring methods separate the change detection responsibility from adaptation responsibility. These are called explicit mechanisms or explicit strategies. Other methods keep them together, and they're called implicit mechanisms or implicit strategies. Over the course of the years, there has been a number of angles explored to address these problems, and there has been a number of methods developed with increasing complexity and increasing success. We collect them under two categories: supervised and unsupervised methods. Within the supervised methods, we have statistical process control-based methods, sequential analysis-based methods, and error distribution monitoring. Within the unsupervised group, we have clustering and novelty detection-based methods, feature distribution monitoring and model-dependent monitoring. Likewise, in adaptation part, as I said, we have two categories, the explicit and implicit mechanisms. And within explicit group, we have windowing, weighting, and sampling. And for implicit mechanisms, we have pure methods and ensemble methods. Now, I'm going to look at each of these angles and representative methods in some detail before I tabulate them and compare. So let's start with the supervised group. And we will start with the statistical process control based methods. The machine learning theory says errors should diminish as the number of samples increase. This is if we're continuously training the model. If we stop training the model, the errors should at least stay constant, assuming a stationary environment. This forms the basis for a number of monitoring methods. And DDM, drift detection method, was one of the earliest ones leveraging this. It models the number of errors as a binomial random variable. As you know, binomial random variables are used for modeling proportions. So the key variable here is P sub t, which is the error rate at time t. So the average number of errors would be mu within a window. Sigma is the standard deviation of the P sub t, the error rate. Now it uses a rule for alerting. And since we said the error rate should go down with increasing number of samples, it looks for the minimum value of the error rate, P min, and the corresponding standard deviation, sigma sub min. And it caches these and compares the subsequent P sub t plus sigma sub t to P sub min plus 3 sigma sub min. Now this looks like a 3 sigma rule, but the standard 3 sigma rule would compare P sub t to the right-hand side. In this case, the rule compares P sub t plus sigma sub t. But nevertheless, this is the rule the authors selected. Subsequently, they did a modified version of this algorithm. They called it the early drift detection method. This one uses the distance between the errors rather than number of errors or rate of errors. The idea is the distance should stay constant as things are stationary. And by doing this, they have a method that is better suited for gradual drift. They again use a rule. The rule is slightly different. And again, since we are looking for the error rate or distance to stabilize as the observations become stationary, we search for P sub max and sigma sub max, cache these and compare P sub t plus 2 sigma sub t to P sub max plus 2 sigma sub max. They set two thresholds. A higher threshold, 0.95, for example, is used for issuing a warning and starting caching the data. And a second threshold, 0.9, for example, is used for sending an alert and resetting the maximum values for P sub max and sigma sub max. So we are not keeping any data. The updates are incremental, so the methods are very efficient. They're constant time and space complexity. However, the published versions of these algorithms require 100% of labels. So if you're working on a cognitive task, a label can cost $1 each. So the labeling costs will add up very, very quickly. So that's the main drawback of these methods. Also, they are prone to false alarms. Next method we're going to look at is the supervised group, the methods. And we have linear flow rates in this group, LFR. The idea is this: if the data is stationary, the contingency table should stay constant. So the contingency table is the confusion between predicted values and the true values. And, we have the true positives if we predicted correctly and that where the true value is 1. And likewise, we have false positive, false negatives, and true negatives. Now, instead of comparing these contingency table values directly, the algorithm calls for calculating 4 rates. As you remember, the recall rate is TP divided by TP plus Fn. And we have likewise the precision rate, the specificity rate, and the P sub PV, for lack of a better name. And PV stands for negative predictive value. Again, instead of calculating these rates from the raw values over and over again, they use an incremental update. The incremental update calls for the current rate, P star stands for recall, precision, specificity, whichever rate you're updating, to be a linear combination of the previous rate and an indicator function that is based on the current label, whether the current label is affecting this rate or not. This linear update is the namesake for the linear 4 rates of the algorithm's name. Now, we test for change in the 4 rates calculated with this formula. Unfortunately, there isn't a closed form formula for the significance level to conduct that test. So we need to do a Monte Carlo sampling to identify the significance levels for these rates. But this is done only once at the start of the run. So it's a fixed cost that can be absorbed. And also we are comparing the 4 rates continuously over the course of this the stream. So these tests are correlated, so there needs to be a Bonferroni correction for these tests to be viable. Nevertheless, we're not keeping any data around. We have an incremental update algorithm. Again, we have a constant time and space algorithm here. And since we are looking for different types of errors separately, LFR is better for class imbalance than DDM or EDDM is. Next, we look at the error distribution monitoring within the supervised group. ADWIN stands for adaptive windowing. And remember, we're looking at we're monitoring the prediction errors with DDM, EDDM, LFR, and also for ADWIN. So I go back to our example, but I change the colors and use blue to indicate correct prediction and pink to indicate incorrect prediction, and also upside down figure for humor. Now it considers, it picks a window W and considers partitions of this window, W sub 0 and W sub 1. For each partition, it calculates the mean error rate, mu sub 0, mu sub 1, and compares the difference, absolute difference, to a threshold based on Hofting bound. As you know, Hofting bound is used for testing difference between means of two populations. Now, it does this test for every partition of that window W. And if it finds any subpartition violates this test, it drops the last element within the window. Now, this is clearly inefficient, but this is the academic version of the algorithm. There's an efficient version also published within the same paper, and it uses a data structure for windows that is based on exponential histograms. Now histograms are based on sliding windows. So instead of dropping the last element, it drops the last window, last subpartition. So it gains some efficiency by the weight computes the histograms and the weight drops the data. The time and space complexity for this version is log W, where W is the length of the window. Now for the loss of efficiency compared to the constant time algorithms that we've seen before, we gain better localization of the change point. I'm gonna talk about resampling here in this group. Resampling uses prediction losses rather than the classification losses. Now, prediction loss is slightly more general. And it compares the prediction loss over random permutations of the data versus the ordered training data. The idea is, if the random permutations is causing performance degradation, there is clearly structure within the order of the data. Hence, there is it's susceptible to drift. Now, clearly, this is not very efficient, but they offer a parallel permutation test, which is still expensive. But this is the only method that is directly applicable to regression setting. That's the reason I wanted to include it here. And also a side note, it doesn't have to be a stream. Even if we are working with a finite training set, then drift could be problematic if what we have in the training set doesn't resemble what we see in the population. And this can happen for big data as well. It doesn't only happen for streaming problems. The Achilles heel, the main problem, main drawback of the supervised methods is the labeling cost. So let's look at the unsupervised methods and see how they address this issue. We're going to start with clustering and novelty detection based methods first. Here we have a number of algorithms that were developed over the course of the time, but they share the same underpinning. The idea is to cluster the incoming batches of data, and each batch is either assigned to a known class or declared as a concept drift or emerging concept. Now, the way these algorithms do this differs slightly. Olinda started with the k-means algorithm. Minas moved to microclusters to gain efficiency by incremental stream clustering. The TechNut used discrete cosine transform to efficiently estimate the distances. Wool Ensemble treats the outliers as potential emerging class centroids. ECS Miner stores and uses the cluster summary efficiently, and GC3, one of the most recent methods, uses grid-based clustering. Now, the pattern you see here is the main problems that the developers were trying to address are the curse of dimensionality with the clustering methodology, and also understanding what constitutes an emerging concept or a concept drift. So clearly these methods are not very efficient, but regardless, this set of methods is the only set that is capable of addressing emerging concepts. So if you suspect emerging concepts in your data, you have no choice but resort to one of these methods. ECS Miner and GC3 are some of the most recent ones in this group. ECS Miner is order of W squared divided by K, where W is the batch size and K is the neighborhood size in KNN. And its space complexity is order of W. So it's not really that efficient. And GC3 is using grid-based clustering, so its time complexity is order of G log C, where G is the grid size and C is the number of clusters, and likewise for space complexity. Clearly, they are some of the most expensive methods, but then again, not using labels, saving dollars, and the only set of group capable of addressing emerging concepts. One minor caveat is they're capable of addressing only clusterable drifts. So population change-based drifts fall out of this group, for example. Next, we look at the feature distribution monitoring. So the idea is, as the title says, we look at each feature separately. So I have in the second axis our toy problem. In the second axis, I have the color feature. And in the third axis, I have the size feature. And we monitor features individually. As I said, we pick two windows, W sub 0, W sub 1, a reference window and a window to compare. And there are many ways to compare. For example, change of concept COC uses Pearson correlation. And HDDM uses Hellinger distance. HDDM stands for Hellinger distance drift detection methods, no surprises. Hellinger distance is like an L2 metric for probability distributions. Now, if we have a lot of features to track, it may be a good idea to use principal components analysis to reduce the number of features. There are different camps in this. One camp suggests using the top 10% of the PCA for monitoring. The other camp finds better results with the bottom 9%. So there's some contention there, but the idea is using PCA to reduce the number of features to track. Hellinger distance has order of dB time complexity, where D is the data dimensionality and B is the number of pins. It's using a histogram-based method. And the space complexity is order of D. So it's efficient enough, and it's it clearly, but it has drawbacks also. It's not capable of addressing population drift, for example, because we're looking at individual features only, and its sensitivity drops with class imbalance. Now, next we look at model-dependent monitoring, and we address a significant problem with this group. Now, the unsupervised methods suffer from high false alarms, high rate of false alarms. This is because they consider any change in the observations they're monitoring a reason for performance degradation. But this is not true, actually. Not all changes matter. The changes near the classification boundary matters for the performance of the classifier. The changes away from the classifier boundary don't as much. So the next set of groups capitalize on this idea to reduce the false alarm rates while keeping the methods unsupervised. So the first method is called the A-distance method. Now it says, let's use the posterior probability estimate if it is available, because it's more general than classification loss. And then it creates a generalized Kolmogorov-Smirnov distance. As you know, Kolmogorov-Smirnov distance is used for comparing two distributions. Here I have a picture of two CDFs, and the KS distance is the maximum distance between the CDFs along the probability space. Now, what they argue is comparison metrics like L1 distance is too sensitive because it's integrating the difference over the probability space, so it's considering all changes, and it's going to be sensitive to the irrelevant changes. So they come up with a generalized version of the KS distance, as I said, which looks at the band near where it considers the changes to be relevant. And this way it becomes less sensitive. And the complexity of this is order of log W for time and order of W for space. Again, W is the window length. So it's comparable to, for example, Adwin without any labels. Next set of groups look at the margin. Since the main issue with the false alarms is whether a change matters or not, these methods say, let's look at the margin directly. So the first set of groups, first paper comes with three sets of comparisons. The first one is a ranked statistic on density estimates for a binary representation of the data. The second one compares the average margins of a linear classifier induced by the one norm SVM. And the third method is based on the average 0, 1, or sigmoid error rate of an SVM classifier. So they, as you can see, all work for classifiers that have a natural concept of margin. So SVM is one of them, logistic regression is another one. But many machine learning models don't have a natural margin concept. So the next paper, MD3, generalizes the margin idea. And the way it does is it embeds a base classifier of any type in a random feature-backed ensemble. A random feature-backed ensemble works this way. For each ensemble member, we pick a random subset of the features and we develop the classifier based on that subset. And then we keep doing this for new ensemble members. Now, the margin is defined as the high disagreement region of the ensemble. Now, this makes sense because if we have an example where all the ensemble members are in agreement, regardless of which feature subset is used, this is clearly an easy classification task. So it's probably not near the classification boundary. Whereas if we have an example where most ensemble members disagree depending on which feature subset is used, this is a difficult classification task, difficult example. So this qualifies for being in the margin. By doing this, by focusing on the margin directly, they reduce the false alarm rates to the minimum possible while using no labeled data. Now, the problem is though, you have to commit to a learning paradigm, and since the learning is bundled up with the concept drift and adaptation mechanisms, it's really difficult to come up with a complexity number that compares these methods directly with the other concept drift monitoring methods. So it's not apples to apples comparison, so I'll leave that out. And next, we look at the adaptation side. As we said, we have explicit and implicit mechanisms. Within explicit, we're going to start with the windowing method. We'll go back to Advin, adaptive windowing. As you recall, it has this windowing strategy where you drop the last sub window if the threshold with respect to the Hofting bound threshold is exceeded. So this, in effect, adaptively window size during the drift. So it already has a built-in adaptation mechanism, and you can use the current window to retrain your model. Another method is just-in-time method, JIT. This is not using labels, and we haven't seen this before. And it has an integrated strategy. It uses cascading sub-windows, W sub 0, 1, 2, 3, 4, for example. And for each window, it looks at the prediction, a statistic of the prediction rather, like the mean of the prediction value or the standard deviation of the prediction value. And it computes the confidence interval. Here in the example, I suggested using the mean of the window and the confidence interval. Then it looks at a set of subsequent confidence intervals. And if it finds a set where the confidence intervals do not intersect or have an anti-intersection, it declares a change point. And for the adaptation part, it goes through a similar refinement process to find the beginning of the change rather than the declaration of the change. So it does have an explicit mechanism for how the adaptation window is defined. The rest of the methods like DDM, EDDM, LFR, and similar methods do not call for explicit adaptation mechanisms. They are designed to detect the change, and for adaptation, you're on your own. Now, I'm going to skip weighting because it's impractical for streams. So we can look at sampling for an alternative for those problems. We have biased reservoir sampling. It's similar to unbiased reservoir sampling or regular reservoir sampling. But when we consider an example for inclusion in the sample, we do not throw a coin and then randomly decide whether to include it or not. We deterministically include it, but we flip a coin nevertheless, assuming the reservoir has a capacity, given capacity, it uses the percentage full of the reservoir and flips a coin by that probability, and it decides to overwrite an existing example or appending to the window based on the outcome of the coin flip. Now, this strategy turns out it implements an exponential decay bias function. And the initial capacity of the reservoir is determined by the decay rate dictated by the bias, this bias function. Now, for the methods which don't have an explicit adaptation mechanism, we can use this strategy. We can keep a biased reservoir, and once we detect a change, we can use the examples in the reservoir to retrain our models because they are biased for the more recent examples. Next, we look at the implicit mechanisms. And within the implicit mechanisms, I'm going to skip the pure methods because the ensemble methods are more powerful and more interesting. So I'll dive directly into them. And within the ensemble-based adaptation, the idea is to train a new ensemble member with each incoming batch of data. And once we identify an ensemble member that is not in agreement with the rest of the ensemble most of the time, we think it may be because it's based on data that is not keeping up with the current state of the data. So we either retire that ensemble member or decay its effectiveness. Now, the advantage is if it turns out that it's a recurring concept, and we're going to encounter this concept again, we don't have to retrain a new classifier because we may already have an ensemble member that is retired or decayed that we can revive to address this issue. So ensemble-based methods are powerful for this unit. They're good for cyclical concepts. As you can imagine, pretty much all of the ensemble-based learning methods have a non-stationary counterparts. We have online non-stationary boosting, non-stationary random forests, dynamic weighted majority, and Learn++ for non-stationary environments. And once again, since the learning detection and adaptation stages are all bundled into the algorithm itself, its complexity is not apples-to-apples comparison, so I'll keep it out. Now we tabulate the methods and look at certain scenarios. DDM, EDM, as we recall, it's constant time, more data stored, but there is a large labeling cost and they're susceptible to false alarms. LFR is again constant time and space, It's better with class imbalance because it uses the different error types separately, but it still suffers from labeling cost. And admin is log W time complexity and space complexity. So it's more expansive, but it's better for change localization, still suffers from labeling cost. But these are the essentially supervised methods available. And so to make these methods useful, we need to address the main drawback, which is labeling cost. So there needs to be some sampling stage, and this is an ideal scenario for using microservices-based architectures to provide that functionality. JIT, just in time, again has log W time complexity. It's doesn't use labels, so it's a great advantage for it. But it's useful only for abrupt changes, unfortunately. It's not good for gradual drift. Nevertheless, it's an interesting alternative. The ECS minor and GC3 are the representatives of the clustering group. As you recall, DCS minor is order of W squared by K in time, and order of W by for space. W is the size of the window, and K is the neighborhood size for K and GC3 is order of G log C, where G is the grid size and C is the number of clusters. Now, the pros include emerging concepts, capability of addressing emerging concepts. So this is, although these are expansive methods, this is a factor that's, that makes them worth considering. If your data is susceptible to emerging concepts, this is pretty much the only set of methods, unless you're dealing with recurring concepts where you can use ensemble-based methods. The drawbacks also include they can address the clusterable drifts only. We looked at the feature monitoring-based methods, feature monitoring methods. HDDM is a good example of this. Its efficiency is order of dB. D is the data size, B is the number of bins for time, and order of D for space. Again, it's using no labels as its main advantage, but it's not suitable for population drift, and it loses sensitivity with class imbalance. Nevertheless, it's a good alternative with low cost and no labels. A distance, as you recall, addresses the high false alarm rate of the unsupervised methods ECS minor, GC3, HDDM. Its complexity is comparable to Advin, the supervised methods. It doesn't require any labels. It reduces the false positives, false alarms compared to HDDM. So it's a viable alternative. Margin and MD3 methods reduce the false alarm rates further by looking at the margin, and MD3 has this very powerful margin concept for general classification models. But you have to subscribe to the machine learning modality that these methods offer. And likewise for ensemble methods, it's capable of addressing recurring concepts. So that's a main advantage, but it uses large batches, so that becomes that could become an issue because large batches means that the changed location will not be identified very correctly. Again, these last two sets of groups, learning, detection, and adaptation, are bundled, so they're not really comparable in terms of efficiency. You must subscribe to the learning modality, but they're the most powerful methods available for you. So, Oliver, I'll hand it to you.
All right, thanks so much, Emre. This was definitely a much more in-depth, detailed analysis of these methods than we've seen before on most of our Lightbend webinars. So thanks so much for sharing with that. Well, folks, before we get to the Q&A, there's a couple pieces of content that would be helpful in even taking quite a step back from what Emre is talking about and discussing more about how do fast data architectures look like and how does streaming play a role, where did we come from. One of these O'Reilly mini books that our VP of Fast Data Engineering, Dean Wampler, wrote is available on our website. Unfortunately, the buttons are not working when I upload the slides, so the best place to find all this stuff is lightbend.com/learn. Emre, I think we have another couple pieces to share. Ooh, fade away. The next one actually touches directly on machine learning models, and this was written by our Fast Data Platform architect, Boris Lublinsky. You may have seen him present for us in the last few months. And he's talking about an element of what Emre is discussing, which is how to serve machine learning models in production. And this touches on the concept of, well, concept drift as well. And finally, the last piece is our general technical overview for Fast Data Platform. It's been recently updated, so you can see all of the good stuff that's coming along with that. This is our commercial offering. We just released version 1.1, and it's a very exciting time for us at Lightbend. And a lot of clients out there have a good deal of interest in what we're doing here. So that's all I have. Let's get to a couple questions. Oh, Emre, this is your. We'll make sure this gets hyperlinked, but this is the references that Emre had from his presentation. There are quite a lot of them. So if you have interest in following up, Emre kindly made us a very exhaustive list of where you can learn about all of these topics that he presented. So we only have a few minutes left, but there were a couple questions. Emre, when we're talking about DDM and EDDM, there's a two-part question. Are these defined for your classification models only?
That is true. They are for classification problems. They're not for regression setting. That's why I included the resampling method as one method that addresses the regression setting directly by considering prediction loss. But there are some other methods like JIT, which look at the prediction, a statistic of the prediction value, and it's a confidence interval. So it may be possible to leverage some of those methods. Or if you have a margin-based regression model, you may be able to extend the work that is done for classifiers with margin. But there will be some research involved in that. Otherwise, in terms of what's available in the literature, only the resampling method is directly applicable to the regression setting. And unfortunately, it's a costly method, although they provide a parallel permutation testing. I didn't include the complexity numbers for that method because in the paper they don't give a concrete algorithm or concrete sense about how the efficient version works, or they have an algorithm, but the worst case scenario complexity of it is not good, obviously. But they argue in the paper that in real life, you don't have to test all these permutations. Only a small subset of these permutations are sufficient, but they don't go into details how small. So it's not easy to come up with an average case complexity for this algorithm without actually implementing it for yourself.
All right, thanks. I'm not sure if the follow-up question to that is clear enough in the context that it was provided, but when it comes to defining errors for such models, is there some sort of best practice to follow for error definition?
I mean, for the classification laws, it's reasonably clear. Actually, it's considering most of these algorithms are considering a binary classification scenario, or actually, all of them exclusively are considering a binary classification scenario. So the classification error is clear there. I have not seen them addressing a multi-class classification problem. So that's a very good question, actually. In that case, a confusion matrix would be useful. So it might be possible to extend the LFR method to cover that case, but with quite modifications, because you wouldn't be looking at a precision rate or recall rate and statistical changes in those rates anymore, but you would be looking at the contingency table values directly, and you would have to come up with the efficient update algorithms for those, and sampling for the significant levels of those comparisons, such and so forth.
All right, well, I hope that answers the question from the gentleman who asked. The final question that we have time for today is, Emre, are you familiar with any machine learning libraries for Scala, with the exception of Spark ML, which I think a lot of people are aware of? Spark ML, coincidentally, is included in our fast data platform, so we support that. But we also encourage our clients to kind of bring their own machine learning libraries. Are there any out there that you have played with that you might recommend to our audience?
I will take it in the context of this presentation, if I may. And this is a great safer. Not because it's safe, it actually brings up a point that I wanted to address. None of these algorithms are unfortunately available in such libraries. EDDM and EDM are available in Samoa, but Samoa is practically dead. So all the other algorithms are either available. So some of them are available in MATLAB, but again, for scalable learning, for stream applications, for big data learning, whatever is available out there is not great. So for the general context, I don't have a clear preference. I just look at the toolbox that I need for the problem. Sometimes R has a good toolbox, sometimes Python has a good toolbox for me. So I don't make a choice for the library, the platform, before I actually decide on what tools I need for solving the problem.
All right. Well, that's all the time we have for today, folks. Emre, thanks so much again for joining us. It was a very revealing presentation. If you're a Lightbend subscriber and you've got some questions that didn't make it to the Q&A, then feel free to send them through our customer portal, and either Emre or someone from our engineering team will actually be able to interact with you. If you or your manager feel like it's time to find out how we at Lightbend can help you ramp up quickly with fast data, streaming, and machine learning, you can simply write to me directly at oliver@lightbend.com, or go to our website and contact us to set up a 20-minute chat with someone. We'd love to hear from you. So again, thanks for joining us and have a wonderful day. Bye-bye.